So I've been reading Introduction to Kolmogorov Complexity and its Applications, and I came across this exercise, which is in Chapter 1, Section 9, Exercise 2. And basically what it says here is its conditions are, it says, suppose we are given a coin with an unknown bias. The probability of heads is p and the probability of tails is 1 minus p. P is some unreal number between 0 and 1. The question is can we use this coin to simulate a perfectly fair coin? Now, this question to me is super interesting for a whole bunch of reasons. But let's go into this and let's understand first what the question is even asking. So the first thing is that it says this word bias, and it gives a brief understanding or it tries to explain what it means by bias, as in that the coin is not necessarily fair, as in that you don't get heads 1/2 of the time, 1 out of 2, a likelihood of 50% of the time. You get heads p% of the time, where p is between 0 and 1. So it could be that this coin comes up heads 0.1 times, or 1/10 of the time, or 2/10 of the time, or 1/1,000,000th of the time. And p is unknown. The rest of the time, the probability, right, if it comes up heads, let's say 1 out of 10 times, then it's going to come up tails 1 minus that value. So 9 out of 10 times if p is 1 out of 10. Now, we don't know, though, what p actually is. So what we need to do, and what they're asking is that we basically don't know with what likelihood this coin is going to come up heads or tails. And then it asks us, can we use this coin to simulate? And that's key, right? What does it mean to say simulate a perfectly fair coin? And basically, it's just saying, can we use this coin to then construct a scenario that we can guarantee is going to occur 1 out of 2 times, or half the time? Can we use this coin to simulate a perfectly fair coin? Like, if we know the bias, we can maybe use that coin to simulate something that's 1.5 times, 1 out of 2 times. We could use that if we know the bias, if we know p. But what's key here is that we don't know p. It's unknown. So how can we do this? And it would just take a moment, just pause this video, take some time to think about whether or not this can be done, and read through this question in detail and see if you get the understanding of this question before it is that I continue. Okay, so now I hope you have thought about it. You paused the video, you thought about what this question is asking, and hopefully you understand what this question is asking before we could go into whether or not it's yes, we can, or whether it's no, we cannot. Now, I love this question for a variety of reasons if we switch into the personal. So one of the reasons why I love this question is because you don't really need to know too much prerequisite mathematics to have an understanding of what this question is asking. It helps if you have some good notions of classical probability, for sure, and there's other things you also might want to be mathematically minded before it is that you can understand this question. But really, you don't need to know any algebra, you don't need to know geometry, you don't need to know calculus, you don't need to know anything. But you could think about this question in a very raw sense if we have just a basic understanding of probability. The other reason why I love this question is just because of how well constructed it is and how interesting the thought experiment of it is. I mean, it also transcends, right? So what is it that makes this question so nice? Well, to me, right, this idea of being given a coin, let's say, where we don't know the bias, right? Like this, and it's an unknown real number, the bias, right? It's unknown. It's basically this coin that we're given where we have is basically saying, here's something that occurs randomly. We don't know how random it is, but we know that heads comes up with some probability, not guaranteed to be heads, and it's not guaranteed to be tails. And it comes up randomly. And with any source of randomness can we then produce a randomness that we would want, which is this question, right? This is, can we use this source of randomness? Can we use this coin, right? A source of randomness to simulate, to create, right, a randomness that we would want, a randomness where we could say, okay, well, this is going to occur half the time. So then therefore we could produce, more, we can utilize that fact. We want randomness in various instances. And that's a few of the reasons why. But then on top of all of this, the next thing that I thought was super interesting about this question is that its answer. And its answer is that yes, we can do this. And now with yes, maybe you want to pause the video and think about why it is that it's yes, or maybe construct how. But the answer is yes, and I didn't come to this on my own. Again, I got this from the textbook, and it says in the question itself, it references where the answer is. So where is the answer? The answer is... So I read, and it says in the comments to this exercise, it says that it quotes the source of this. So the source is J. von Neumann. Von Neumann. And it's called Various Techniques used in connection with random digits. Used in connection with random digits. So I looked up this source, and I looked up where they got this question from, because this isn't I read this exercise in this book, and it's not the original place where it was referenced to. It was referenced to originally, or they got it from, at least not originally. Probably it's been posed somewhere else, but who knows. The source that they got it from is from J. von Neumann, who was a mathematician, and he wrote this paper, Various Techniques Used in Connection with Random Digits. So what did I do? I went to Google, I typed in, let's just type in various techniques, if I could write. Oh, wait, I have a keyboard here, so maybe that'll speed things up. Various techniques. Oh, wait, why isn't the keyboard working? No. Do I have to put this down? Let's see. Keyboard not working. Various techniques. Oh, citing a rare paper. Various techniques used in connections. Okay, let's see if this will just come right up. Oh, no. Okay. So let's see. Let's use that fact. Of course, it's still not working. Various techniques. Okay. Used in connection with random digits. Okay, good. All right, and then let's see. Now let's see if this is the one that... Here we go. Beautiful. Okay, so now I started reading this paper, and I read through this paper, and some of it I still don't understand, so maybe some of you can help me in explaining some of it. But basically, he asked this question. He says, how can one... So here's A, right? If we read here, can I highlight that where I am? Oh, yep, I can. Okay, so we see A here, right? How can one produce a sequence of random decimal digits, a sequence where each digit appears with probability 1/10 and where consecutive ones are independent of one another in all combinations? Now, here he's just asking for a random sequence, okay? He wants a random sequence of decimal digits, so the digits between 0 and 9. And then he says, on problem A, I shall add very little to what has been said earlier in this, blah, 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 two quantitatively different methods. Okay, physical processes and arithmetical processes. So physical processes, something like in quantum theory, there's random phenomena, right? Like where an electron's going to be, the wave equation, stuff like that. I'm not too sure. But there's allegedly random, quote-unquote, processes in physical processes. Or we want to identify what or we speculate that there's random physical processes. And then there's arithmetical processes, which are just processes that we construct in order to produce a random sequence. Now, it basically says that the main characteristics, blah, 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 blah. One difficulty is never quite sure what the probability, and this is where it is that we have our question coming up. So one difficulty, if we read from here, one difficulty is that one is never quite sure what the probability of occurrence of the nuclear accident. Right. This difficulty has been overcome by taking larger counts than one in testing for either even or odd. To cite a human example, in tossing a coin, is it probably easier to make two consecutive tosses independent than to toss? Okay, so this is just basically, he's just going through the probabilistic aspect of this, and he's saying it in a higher level language than what it is that I'm trying to communicate in this video. So basically, if we read here, right, it says, if independence of successive tosses is assumed. So in our coin that we have for our question, right, we're assuming that when I toss it once, it has no bearing on the next tossing, which is basically this independence criteria, that this independence of successive tosses. So let's highlight what's going to be key here. Whoa. Okay. So if independence, you see? Okay. So here we go. This part here. Okay, so don't ignore what was highlighted over there. It says, if independence of successive tosses is assumed, we can reconstruct a 50-50 chance out of even a badly biased coin by tossing twice. If we get heads, heads, or tails, tails, we reject the tosses and try again. If we get heads, tails, or tails, heads, we accept the result as heads or tails. And this process is now unbiased. So this is our answer. From here, right, from that dot to the next one is our answer to how this is done. So I'll highlight it again, okay, and I will go through this answer with you. So if independence, and again, we have independence in our coin, okay, we know that the previous flips have nothing to do with the current flip. So that's independence. Okay, we can reconstruct a 50-50 chance out of even a badly biased coin by tossing twice. If we get heads, heads, or tails, tails, we reject the tosses and try again. If we get heads, tails, or tails, heads, we accept the result as heads or tails. So basically, what this is doing is that you have it where you have this coin, and what you're going to do is you're going to flip it twice. If you get heads, heads, then you reject. You don't care. That does nothing to simulate our coin. If we get tails, tails, that does nothing. We reject. But if we get tails, heads, or heads, tails, we take this as tails, and we take this as heads. And basically, what Newman is claiming is that if we do that, then this will occur 50% of the time. Or now here I'm going to start with our lesson on just some classical probability, because at first I did not believe what he was saying here. I did not believe that this would be heads, that this would simulate a 50-50 chance, or that this would simulate a fair coin. I did not deem this a solution, so I had to convince myself. So to convince you, I am going to go through a basic rundown of what's in classical probability. And one of the things that we need to understand is conditional probability. And conditional probability of something is basically finding the probability of a given event if you know a certain event has already occurred. So it's written the probability, that's P, and then you put in parentheses A, the probability of event A, and you put this slash here to say given that B has occurred. And it's equal to the probability that A and B both occur over the probability that B occurs. And this formula, it's not arbitrary at all. It actually makes pretty decent sense if we consider, right, like let's say we know that a random dot will appear somewhere inside this box. Okay, this is the universe. The random dot is guaranteed to appear somewhere in this box. it makes sense to say that the probability that it lands inside this circle A is the area of this circle divided by the area of the entire box, right? That's the probability that the dot, if we know the dot is guaranteed to land somewhere in this box, including somewhere in A, that circle A, it makes sense to say that the probability that the dot lands inside A is the area of A, the area inside this circle, divided by the area of the entire rectangle. That should make sense. Now, if I say that this here is the circle B, right? If I want to know the probability that the dot lands inside A, given I know that the dot is somewhere inside B. So I know that the dot is somewhere in here, right? What's the probability that the dot lands inside A? Well, the probability that the dot lands somewhere inside A, you should convince yourself, is just the probability that it lands in both, which is this region. This is A and B. A and B. Over the probability of B, which is just this region here, that circle. And that's sort of justifying this formula. It's a basic rule of classical probability. And with this fact, we can actually justify and see how it is that the solution that Newman proposes to this is true, because what we're asking, or what we're saying here, is that what is the probability of a heads tails given that we know either a tails heads has occurred or a heads tails has occurred. So a heads tails has occurred or a tails heads has occurred. And if we follow from our conditional probability rules, we see that this is the probability that, right, what takes the role of A is the heads tails, and then B takes the role of the heads tails or the tails heads. So this, right, the probability, or I should write it out, heads tails and, right, heads tails or tails heads, right? And what divided by the probability of heads tails or tails heads, right? And we need to first see that this, right, what is this one here, the top one. The top one, we just need to convince ourselves, is actually just the probability of heads tails. Because if you think of it in terms of sets, A and A or B, right, that's just A, if we think of that, right? So if we look at this picture again, let's say that this is B over here. A and A or B is just A. It is what? So A or B is everything, and then A is the intersection between the two. Isn't it this piece? Yeah, I think that's right. So let's see. Go through this with me. Take my time. Check me. Make sure I'm doing everything right. So I believe that it's just this piece then, right? So we want to convince ourselves of that this is just the probability of A and B. And in that case, what is it here? So I want to show that this is the same thing. Are these two the same? A and A is just A. And then A. Why am I drawing a blank here? So what is this? This is A and intersect A union B. What is this equal to? This is equal to A union B, A intersect A union B. Why am I drawing a blank here? Someone help me out. This is just A. This should just be A. Why though? So with these two sets, the question is in set theory, you want to say A intersect A union B. A. In set theoretic notation. Why? So if X is in here, right? I need to convince myself that it's in here. So if X is in here, it's in both of these, so it's in A. If X is in A, then it's in this one and it's in this one. So these two sets are equivalent, and this is just A. And then therefore, this probability is just the probability of a heads tails. Because this took the role of A, this is like A, this is B, or it takes the role of a union, and is called an intersection. But you should see the probability of a heads tails and a heads tails or a tails heads is just the same set as a heads tails. What happens if a tails heads? Can a tails heads? If a tails heads? No, if a tails heads occur, then this isn't good. Because if a tails heads occurs, then it doesn't matter because it's not and, right? A tails heads occurring makes this true, but it won't make this one true. And that's why it's just A, which is good. So it is just the probability of A. So the top part just becomes the probability of a heads tails. And we have that part done. So make sure that I'm doing this right. The probability of a heads tails and a heads tails or a tails heads, we should see over the probability of a heads tails or a tails heads. And we should see that that's just the probability of a heads tails on the top over the probability of a heads tails or a tails heads. Now, the next thing that you want to do with is this denominator. Now, the whole thing here is that if we flip the coin twice, right, we have only 4 different possible outcomes. We have a heads that could occur. We could have a tails that could occur. We could have a tails heads or a heads tails. Now, in classical probability theory, we should know that these are the 4 distinct outcomes, and we should see that the sum of all of these is 1. Okay, that's a theorem from classical probability. Again, these are all the possible outcomes. Even for our heavily biased coin, it won't matter. These are all the possible outcomes. Whatever the probability of each one of these is, the probability is 1. But what's key here is to notice that these events are independent of one another. And basically that the probability of a tails head or the probability of a tails heads or heads tails, right? The probability of this is the key thing that we need to convince ourselves of. This one, right? That these are disjoint is the word. Plus tails heads, right? That's what we need to convince ourselves of. So I could rewrite this now as this. And again, at this point, classical probability is extremely useful to understand these notions. If not, it would be very difficult for you to follow this. But I should convince you that these two, a heads tails and a tails heads are disjoint. You can't have both of them occur in 2 flips, right? You're flipping the coin twice. You could get either a heads tails or you get a tails heads, and you can't get that event. Those 2 events can't occur simultaneously. So they're disjoint, and that's why you can split them up into the 2 respective probabilities. Now let's go ahead, and now we're on to the phase where we just compute probabilities. And now, what is the probability of a heads tails in a 2-coin flip? Well, that's simply the probability, since these flips are independent. You could use the fact that these flips are independent. So it's just the probability. Homestead. It's just the probability of a heads times the probability of a tails. And then that becomes the probability of a heads times the probability of a tails plus the probability of a tails times the probability of a heads. But at this point, you're pretty much home free, because now you should see that this is something, right? Whatever it is. The probability of heads we know is P. The probability of tails is 1 minus P, but that's not even necessary, because we should see that this is the same thing as this. So there's 2, the probability of heads times the probability of tails over the probability of heads times the probability of tails. And then this cancels, and then this cancels. And you wind up with this being a probability of 1/2. And that's exactly what we wanted. He simulated a fair coin. And what that looks like in summary is as follows. Basically, what you do is you say, okay, I want to simulate a fair coin here. So I have this coin in my hand. I don't know its bias, right? It has some bias, this coin, right? Here's my coin. And I'm going to start flipping it. And basically every time that it comes up heads, heads, or tails, tails, I reject. I don't care. But the first time, right? So I could say, me and you I'm saying, okay, we don't know. We both don't know. I'm being very transparent. I'm saying, I don't know what the bias is of this coin. I know that it comes up heads with probability P. And you're like, all right, well then, what are we gonna do? Because we wanna start gambling, me and you, right? And I say, okay, what we'll do is we'll flip this coin twice, and if it's heads, heads, we reject, and if it's tails, tails, we reject. But if it's heads, tails, we accept this as heads. And if it's tails, heads, we accept this as tails. And I tell him that makes it so any time, so we keep rejecting if it's heads, heads, and tails, tails. But if it's heads, tails, we take that as heads. Okay, we flip it twice, and we keep doing this. And I tell him that this will simulate a fair coin. And you should convince yourself that this actually will be a fair coin by the argument I just made. Because it's essentially the probability of a heads, tails, given that we have a heads, tails, or a tails, heads. And that's the same thing as the probability of a heads, tails, and by conditional probability, classical probability, heads, tails, and a heads, tails, or a tails, heads, divided by the probability of a heads, tails, or a tails, heads. And then the top part is just the same thing as the probability of a heads, tails. The bottom is the probability of a heads, tails, plus a tails, heads, right? And then this, okay, you could see if we use the fact that the first flip being heads has no bearing on the second flip. So this is the same thing as the probability of a heads times the probability of a tails. And the same thing goes for the denominator. And then that makes the denominator equal. So it's 2 times the probability of a heads, tails. Oh, we don't even need to use the fact that they're independent. No, you would need to say, yeah, because you don't know if the probability of tails, heads is the same thing as heads, tails, if the coin is not independent. So we can't say this. We would have to say that then it is the probability of a heads times the probability of a tails, and then we know that multiplication is commutative, so it's the probability of heads, probability of tails over here, and then this all simplifies to 1/2. And that's exactly what we wanted, that the probability of a heads, tails, i.e. getting a head, we're calling this a heads, we're simulating a fair coin, is 1/2, which is exactly what you wanted. And again, this is like super interesting, back to what I was saying originally, to me at least, on a personal level, which is just, that you can, if we're given something that we know is random, but we don't know how random, we don't know anything else, we just know that it occurs randomly, we can theoretically use that source of randomness to simulate a randomness that we would like, which is 1/2. And you could use now the sequence that you get here, this sequence that occurs with heads half the time and the sequence that occurs with tails half the time, to get any probability you want, I believe, or other probabilities is the word that was used in the same book that I'm reading. So, it's interesting because, again, we're given a random source. It looks like we could then use that random source to get a random source that we would like. And a part that I don't understand is what he's saying over here. He says that he talks about, he says that we see then that we could build a physical instrument to feed random digits directly into the high-speed computing machine and could have the control call for these numbers as needed. The real objection to this procedure is the practical need for checking computations. If we suspect that a calculation is wrong, almost any reasonable check involves repeating something done before. At that point, the introduction of new random numbers would be intolerable. I think that the direct use of a physical supply of random digits is absolutely unacceptable for this. Yeah, I don't understand, you see, what he says here. Because to me, it seems like that if we have a physical supply of random digits, then by what he said before, that this should be acceptable as a source of randomness and that we could use this. But I don't know. I think that the direct use of a physical supply of random digits is absolutely unacceptable for this reason and for this reason alone. And then he says that he goes on to the mechanical procedure. But I don't understand what his argument is here. So I'd have to read through this again and maybe make sense of why it is that if we're given the direct use of a physical supply of random digits is absolutely unacceptable. I don't know why. I'd have to read through this argument again. Maybe you guys could help me. Maybe you guys could look up this paper and explain to me in the comments any mistakes I've made in this video, any misunderstandings, any assumptions I've made. And you could explain why he's saying that he rejects the use of a physical supply of random digits. Because it seems like if we have a physical supply of random digits, that then we can use that, even if we know very little, we don't know its bias, we don't know what the likelihood, it seems like we could use that source for, a fair coin.